Hello, good evening to all of you.
Good evening, sir.
Am I audible?
Yes, sir. Yes, sir.
Okay, fine. Is my screen visible to you?
Yes, sir.
Yes, sir.
Okay, please answer your attendance. Aditya Kumar,
Present, sir.
Anand Kumar, Arnachalam,
Present, sir. Sir,
Azim?
Present, sir.
Okay. Hemant,
Present, sir.
Jagan,
Yes, sir.
Kesav Prasad,
Yes,
Lakshmi Narayan.
Yes, sir. Yes, sir. Present, sir.
Kesav Prasad, okay. Lakshmi Narayanan,
Present, sir.
Prabhakaran,
Present, sir.
Prem Vinayak,
Present, sir.
Rahul,
Yes, sir.
Rajan Kumar,
Yes, sir.
Sabish Kumar,
Present, sir.
Satish Kumar,
Present, sir.
Titus,
Present, sir.
Malish,
Yes, sir.
Vigneshwaran,
Present, sir.
Jayraj,
Yes, sir.
Vikash,
Present, sir.
Vivekanand,
Present, sir.
Yadav, Yuvraj.
Present, sir.
Okay, there is one absentee, Yadav, today. Okay, welcome back. We are in chapter 3. We have discussed in this chapter about SI engine combustion. The last class I have started discussion on the CI engine combustion. As I said earlier, we are going to follow the same sequence. Hello? Is there anything you said?
No, sir. No, sir.
Yeah, I received some feedback. Okay. Please mute your mic. So we have discussed SI engine combustion in this chapter so far, and yesterday's class I started CI engine combustion. For CI engine combustion, I will follow the same sequence of contents as we have done for SI engine. So I'll start with the overview, and then I'll discuss about the different stages of CI engine combustion. Then we'll discuss the factors that influence different stages of combustion. As I said earlier, we are characterizing combustion even in terms of different stages, and then we will bring out various factors that has influence on the different stages of combustion. The idea behind this is we want a progressive combustion in that should proceed in a controlled manner, so that we can improve the performance of the engine and reduce the pollutant that are emitted from the engine. So that's the overall idea. So we will follow the same sequence to understand the combustion process of CI engine as we have done for SI engine. I will also talk about knocking combustion in CI engine. Then I will conclude this chapter with a discussion on combustion chambers for CI engine. So in the previous class, I have given an overview of combustion process in CI engine. As we have discussed, CI engine combustion is a self-ignition based combustion. And for ignition, you are maintaining a high compression ratio. That's why these engines are formally referred to as CI engine, compression ignited engine. So the self-ignition or auto-ignition is initiated because of the compression process. And we introduce fuel very late during the end of compression process. We are introducing fuel at a higher pressure. And what we have in the cylinder, compressed air. So compressed air is the source for igniting the fuel, and of course fuel and air has to be mixed in the ignitable range. Combustion, as I said, cannot be initiated if you don't have ignitable mixture, if you don't have ignition temperature. A proper combination of ignitable mixture and ignition temperature are required. Maintaining a high compression ratio, it's almost twice compared to SI engine. In CI engine, we maintain 2 times higher compression ratio. So maintaining high compression ratio is important from the perspective of igniting the fuel as soon as we inject. So there is a small time delay. After the time delay, the fuel should ignite, self-ignite. Before that, it should reach its ignitable range, and there should be an ignition temperature available in the cylinder. So compressed air is a source for ignition. That's why we designate this category of engines as compression ignited engine. Okay. And then I have just started this stages of combustion in CI engine. Today I'm going to continue that. So what we have seen, so we are injecting fuel at high pressure into combustion chamber where we have high pressure, high temperature air. The liquid phase fuel get into gas phase and then prepare with air in the required proportion. After it reaches ignitable range, and if the ignition temperature is available nearby, the fuel will start to ignite. Generally, ignition happens around the periphery of the spray. You could see that there are n number of sprays. Around the outer region of the spray, that is periphery of the spray, ignition happens because outer region is where you have air interaction initially. Okay, so that is where you will get ignitable range and you have air at a higher temperature. So you have a combination of proper ignitable mixture and proper ignition temperature. So ignition will get started in the outer region, periphery of the spray. And then once the ignition gets started, it will spread throughout the spray region, as you could see here in the final image. So ignition spread and the burning of the entire fuel air mixture will start to happen. Okay, that is how the combustion event proceed in a CI engine. And we have seen this pressure profile that we use to analyze the combustion event. Then there is a heat release rate profile. In fact, the stages of combustion is clearly visible in the heat release rate profile. That's why it is shown separately in the second plot. You have one more profile here. This one, dotted line, is the injection profile. So you could see that there is the fuel, which is a mass of fuel that is injected into the engine cylinder. So this is called injection rate shape or injection profile. Okay. And if you integrate this injection rate shape over this period of time, injection start here. Okay. And then it continues until this period of time, then it ends here. So this is start of injection, this is end of injection. And if you integrate this profile, what you will get is the fuel that is injected into the engine cylinder. We already discussed that in a CI engine, you are controlling load by varying the injected fuel mass. Air mass in the cylinder is constant. You don't have any throttling as we do in SI engine. That is how you control load. In SI engine, you have a butterfly type throttle valve. With that, you are regulating the quantity of mixture. Here, you are not regulating quantity of mixture. You are actually regulating the quantity of fuel through the injection rate shape, as you could see here. At high load, you have to inject more fuel. At low load, you have to inject less fuel. And it is unthrottled operation. The total air that goes into cylinder remains almost constant at different operating condition. What we change is we are changing only the fuel quantity. So the fuel air proportion inside the cylinder is going to be different at different load. That's why CI engines are also called as quality governed engines. SI engines are referred to as quantity governed engine. So SI are quantity governed. CI engines are referred to as quality governed engines. So here you control the quantity of the fuel air mixture that goes into the cylinder by having a throttle valve. So with throttle valve, you are controlling the fuel air mixture quantity that goes into the engine based on the operating condition, load and speed. Here, you don't have any throttle valve. Air is allowed as it is. Air mass, you allow maximum air quantity into the engine cylinder, right? And what you are controlling here is the quantity of fuel that is injected or sprayed into the engine cylinder. So this m dot f is what is a variable. This air mass MA is constant. This is constant. This is variable. So when you vary quantity of fuel in a given mass of air, what is going to change? What is going to change when you change the fuel quantity, keeping air quantity as constant?
Air to fuel ratio.
Air fuel ratio, sir.
What is that air fuel ratio? You said air fuel ratio, right?
Yeah, richer mixture.
So can I say that phi?
Of course, sir. Of course.
Phi represent the fuel quantity. That's why we always use this phi to analyze engine operating condition, okay, rather than air fuel ratio, because it also connects theoretically correct proportion and actual proportion. So phi represent the actual fuel mass that goes into the engine. That's why we use this parameter often to analyze the engine operating condition, okay. So later on also in the second module, emission module, we will talk about how the pollutant vary with respect to phi, because phi captures the actual fuel mass that goes into the engine in each cycle. So it's one of the important variable, okay, we use to analyze pollutant as well as combustion. So in a CI engine, since we are changing only fuel quantity, keeping air mass as constant, phi is going to change. Okay, phi is referred to as quality of the mixture. Quality of fuel or mixture is defined by phi. That's why CI engines are quality governed engines, and SI engines you don't change phi. Okay, phi is going to be fixed, but what we change is the proportion of fuel and air both. Right, at a given operating condition, fuel and air quantity. The total quantity of fuel and air that enters into the engine is varied by using throttle valve. Before that, you already have a fixed air mass and a fixed fuel mass. Okay, so phi that you fix based on air mass and fuel mass, and the quantity of that mixture, air fuel mixture, going into the engine cylinder is varied using this throttle valve. That's why it is called quantity. You are regulating only quantity. Here you are regulating quality of the mixture. So with that note, let us look at the different stages of combustion in CI engine. As you could see here, the combustion happens with 4 distinct stages. This is stage 1, ignition delay period. Then you have premix combustion phase. This is stage 2. You have mixing control combustion phase. This is stage 3. And then the final stage is called afterburning stage or late combustion phase. So this is stage 4. Now let us look at what is happening during these 4 stages. Fuel injection start here and it ends here. Okay, so during the combustion event, the injection event is also continuing in the CI engine. This is how it is different from what is happening in SI engine. In SI engine, end of injection is well before the start of spark discharge. After spark discharge, the combustion event happens, and fuel will be injected in a port injection system in SI engine. End of fuel injection, fuel is injected during intake stroke, right? Here we are injecting fuel during compression stroke. You could see here, this is top dead center position. This is minus 10 degree. This is minus 20 degree. So you are injecting fuel at point A. So point A is typically between minus 10 and minus 20 degree crank angle. So minus is used to indicate that the compression TDC is yet to be reached. Positive value will be reached. Positive value will be used after the piston reach TDC and move down during the expansion stroke. So this is expansion stroke. This is compression stroke. So here this is standard notation. You use angle with a negative sign. Here you use angle with a positive sign. And this is a compression TDC point, which is a reference point for analyzing the combustion process. So injection event starts between minus 10 to minus 20, typically around minus 15 or around minus 20 degrees Celsius before the piston reaches top dead center position. So it's almost end of the compression event. That is where you are injecting the fuel. Okay, so and then with a small time lag, the combustion event is starting at B. That is the region where the combustion gets started. So if you draw in the pressure profile, if you draw motoring profile and firing profile, that is the point where the firing profile deviate from motoring profile. This is similar to what we have done in our SI engine analysis, combustion analysis. So point B is where the firing pressure start to deviate from the motoring pressure. But it is better captured with the heat release plot. That's why we are analyzing with heat release plot here. And there are different criteria used to indicate start of combustion. So this is start of combustion, point B. Point A is start of injection, SOI. This is SOC. There are different criteria followed to get start of combustion. I will talk about it in the next chapter in the combustion analysis. But here the criteria chosen is the zero crossover point in the heat release, is considered as a start of combustion.
Sir, can you repeat that? I'm sorry, sir. Can you repeat that?
So
sentence,
point B is the start of combustion point. Okay, AB is stage 1. Okay, stage 1 is ignition delay time. 0 crossover point means this is 0 heat release, right? This is 0 heat release. B is where the 0 is being crossed and you are having a positive heat release. Okay, so this positive heat release is primarily because of the combustion event. Did you get what I'm saying?
Right, sir. Right, sir.
Initially, so you are injecting fuel here at point A. Okay, and we are considering B as start of combustion. And the criteria we followed here, there are different criteria. One of the criteria is 0 crossover point of heat release is taken as start of combustion. But what you can observe here is after you inject fuel, the heat release is negative. You could see there is a dip in the heat release, then it becomes positive. So this is negative slope, this is positive slope. Okay, sometimes this is also taken as a criteria for start of combustion. But here we have considered 0 crossover point. I will talk about different criteria being followed to consider start of combustion. It's one of the important parameters. Okay, in the next chapter, I will talk about it. But for our discussion, let us consider that B is start of combustion, where the heat release crosses 0 value. Okay, my question here is why there is a dip in the heat release after the fuel is injected. Can anyone tell me?
Because fuel is taking the latent heat of vaporization.
Exactly. So you are injecting liquid phase fuel. You are injecting liquid phase fuel. What you have here is air. Combustion is gas phase. All these liquid particles or parcels have to be converted into gas phase. So you need energy, thermal energy. That thermal energy is latent heat of vaporization that is taken from air. You don't have any other energy source here in the cylinder except air at a higher pressure, higher temperature. So basically the energy is taken from the cylinder. What you have in the cylinder? Air. So air is providing the latent heat. After absorbing latent heat, the fuel is getting into gas phase. Otherwise, there is no combustion. So the dip in the heat release that you see here is primarily because the thermal energy is absorbed. Rather than releasing the energy, thermal energy is absorbed. That's why you have an initial dip in the heat release. After this point, you could see that it is becoming positive. Energy release is becoming positive, meaning the combustion gets started here. That's why there is a change in slope from negative to positive. Okay, there is an energy release. That's why from dip, it is rising up. Okay, and initially there is some uncertainty in this region. That's why rather than taking this point, it is 0 crossover point is taken as the start of combustion crank angle. Okay, the associated crank angle is start of combustion. So we have already discussed about this ignition delay, which is stage 1 of SI engine combustion. If you recollect in the very first chapter, when we discuss about the effect of fuel and its properties on the combustion event, we have discussed about this ignition delay. There are two delay time here. One is physical delay and other one is chemical delay. So the overall delay time is physical plus chemical delay put together is the overall ignition delay time. Now, what is this physical delay that we have discussed earlier?
Time required to make the combustible charge.
Time required to prepare ignitable charge. Ignitable mixture, fuel or mixture. Okay. Time required to prepare ignitable mixture. So basically during this physical delay time, we are getting this P ignition with T ignition, right? Until this, there is no combustion at all. So you are ensuring during this physical delay time, you are ensuring that you have sufficient P ignition and T ignition. Okay, so after this, the fuel is not going to ignite. So the processes that takes place during the physical delay are, we discussed in the overview also. You are injecting liquid phase fuel. It absorbs latent heat, get into gas phase. So before that, there is a breakup of fuel film at the outer spray periphery. That is what is atomization. Once the fuel break up, air will enter in and provide the latent heat. Then fuel vaporize. After vaporization, there is a mixing. Okay, fuel and air mix and reaches this ignitable proportion. Right, for this ignitable proportion, you also need ignition temperature, right, to ignite the mixture. So this is what is happening. You are preparing ignitable mixture from the injected fuel parcels. That is what is happening during this physical delay time. And this is primarily governed by important fuel properties. We already discussed about all those in the first chapter, if you recollect. And then you have chemical delay. You have ignitable mixture, but it takes some time to initiate the ignition. And that time is referred to as chemical delay. What is happening during this time?
What's the formation of radical?
Radical. So this time is basically taken to break down the stable fuel molecule and form radical. So this is basically time required to form radical to initiate the combustion event. Stable molecular structure will be broken down and radicals will start to form. It needs some time for that process. That time is considered here as a chemical delay time. And this is primarily governed by the fuel molecular composition and the kinetics, chemical kinetics. That's why it is referred to as, it's completely a chemical process. That's why it's designated as chemical delay. Okay, so we have already discussed that when you do research on optical engine, they will track OH radical formation is an indication of start of ignition. Okay, it's one of the important indication of start of ignition or start of combustion. Okay, so when you do research on optical engine, they will track the time at which this OH radical is formed. Right, the time at which the OH radical is formed is considered as start of combustion time in terms of crank angle. Okay, so they will closely observe the radical formation, OH radical formation time. So the associated time delay is chemical delay. So in the first stage, from A to B, this is what is happening. There is a, after you inject fuel, there is a time delay. There is a time delay. Okay, and during that period of time, you are preparing ignitable mixture and then you are forming radical. So combustion gets started, okay, and then it proceeds. The second stage indicated here as BC. This is referred to as premixed stage or uncontrolled combustion phase. This is also called rapid combustion phase in a CI engine. That is from B to C. This is a rapid combustion phase. So how this happens, this rapid combustion phase happens is whatever fuel you have injected during AB, the fuel that is injected during this stage AB is pre-mixed with air. Okay, this is what we said happening during the ignition delay time. You are preparing ignitable mixture. So the quantity of fuel injected during the delay time will decide the quantity of ignitable mixture prepared during the delay time. Whatever fuel or mixture prepared during the delay time burns almost instantaneously. That's why it is called uncontrolled combustion. Okay, the energy release during this stage depends on what?
Time interval, sir. Is it
primarily dependent on the delay time?
Yes, sir, of course, of course.
So when you have a longer delay time, this is ignition delay. When you have a longer delay time, you will have more intense premix phase. So this will be further higher. Okay, so the energy release during the premix or uncontrolled phase is dependent on how much of fuel is injected during the delay time. That is dependent on the duration of the delay time. When the delay time is longer, you are going to have a more intense premix phase. When the delay time is shorter, you will have a less intense premix phase, something like this. So this profile, the premix energy release profile, is a strong function of ignition delay time. Longer the delay, more will be the premix phase. Shorter the delay, less will be the premix phase. Now you recollect what I have said earlier about CI engine combustion. It's a quality command. To vary the load, you are actually varying the injected fuel mass. To vary the load, you are varying the injected fuel mass. Suppose if you have a longer delay, then most of the fuel would have been injected during the ignition delay time, and most of the fuel would have burned during the premix phase. Then comes the next stage, which is called diffusion stage, that is indicated here as C to D. C to D is stage 3, which is diffusion or controlled combustion phase. Okay, the duration of this diffusion combustion depends on what?
Turbulence, sir.
The duration of diffusion phase depends on the duration of the delay time. When you have a long delay, you have most of the fuel burned during the premix phase. Very little fuel will burn during the diffusion phase combustion. When the delay time is shorter, you will have a less intense premix phase, okay? Because total fuel mass is constant. Always remember that the fuel mass is dependent on engine load and speed, okay? So you have a constant fuel mass based on the engine load. So this is constant. So when most of this fuel is injected during the delay time, meaning if ignition delay is longer, okay, premix phase will be more intense and diffusion will be less. If ignition delay time is shorter, premix will be less and diffusion phase will be more, because these are happening one after other. So it's happening in a sequence. Right, so the third stage is diffusion burn stage. During this stage, already you have higher temperature and pressure inside the cylinder. So the fuel that is injected during this diffusion phase, okay, so you have start of injection happening here, end of injection happens somewhere here, right? That's what we have seen in the other plot. So end of injection is happening here. Okay, this is where the start of injection is happening. And this is delay time. Okay, after the delay, you continue to inject fuel until this point of time. So this is where you are ending the fuel injection. This is end of injection. Okay, so fuel injection continue to happen even after the start of combustion. Whatever fuel injected here only burns in the premix phase. The rest of the fuel injected is burning in the mixing control phase. Okay, so since you already have this premix phase happen in the engine cylinder, during the diffusion phase combustion, the pressure and temperature in the cylinder will be high during the stage of combustion. So vaporization is not a problem here, because already you have a higher pressure, higher temperature due to the heat release in the premix phase. So the fuel injected during this period of time will immediately vaporize, because you already have sufficient pressure and temperature for vaporization in the cylinder. But what will limit the progress of this stage, stage 3? You have higher pressure, you have higher temperature, fuel will immediately vaporize. But what is going to limit the burn rate?
So turbulence in the combustion chamber.
Turbulence and associated, can I say mixing? How quickly the fuel, vaporized fuel mixes with oxygen is going to decide the third stage of combustion. You already have high pressure, high temperature, fuel immediately vaporizes. But what limits the progress of third stage is the rate at which the mixing of fuel and air, or more specifically fuel and oxygen, right? How quickly fuel finds oxygen and mixes with it within the ignitable range is going to govern the rate of progress during diffusion phase. That's why this is a slow burn phase or controlled combustion phase. That's what is indicated here. The controlled combustion phase is happening primarily because fuel has to mix with oxygen within ignitable range. Otherwise, there is no combustion at all. You already have a higher temperature, vaporization will be quick, the physical delay will be quick. But what will limit is the fuel has to find oxygen, mix with it within the ignitable range. Okay, then only the combustion event can proceed in the diffusion phase. So the rate at which the burning takes place during this third stage is controlled by the rate at which the fuel is injected, that you are externally controlling. So the injection rate shape, whatever I have shown, is going to govern the rate of burning in the third stage. So you can precisely control the rate of burning in the third stage, which you cannot do here in the second stage. This is uncontrolled, but this one is controlled. You can control it by controlling the rate at which the fuel is injected. Okay, and that will govern the rate at which the fuel mixes with oxygen, and that's going to govern the burn rate. So this is how the third stage of combustion is happening. That's why it is called diffusion. Fuel and oxygen has to diffuse, mix within the ignitable range, then the ignition happen. And you can control this phase by controlling the rate of the fuel injection. So at the end of stage 3, almost 80% of the total heat will be released. Even after the end of fuel injection, you could see that there is a final stage, DE. DE is the final stage. Stage 4 is called after burning or late burning combustion. So this is a late burning phase, combustion phase. It happens slowly. After the end of fuel injection, the unburned or partially burned fuel will start to burn, right? Based on how quickly it mixes with oxygen. Okay, unburned or partially burned fuel present in the cylinder will start to burn in stage 4 based on how quickly it mixes with oxygen. So again, the last stage is governed by mixing that happens between fuel and oxygen. This is going to decide the combustion progress in the last stage, and this generally happens at a very slow rate because this is during expansion stroke. Pressure and temperature has dropped in the engine cylinder. Okay, so the mixing between fuel and oxygen is what is going to govern the final stage. That's why it is called a late burning phase or after burning phase, because this happens after the main combustion event. At the end of stage 4, almost 97% of the fuel total heat is released, and around 3% of the fuel energy will be carried away by the exhaust. Okay, 3% of the energy will be carried away by the exhaust. So this is how the combustion event takes place in a typical CI engine or diesel engine. You have a delay time followed by premix phase combustion that depends on the delay time, followed by diffusion phase combustion. This is dependent on how much of fuel is burned during premix phase. Then the final stage that happens after the end of fuel injection. It happens slowly. Unburned or partially burned fuel will mix with the oxygen and start to burn slowly in the final stage. So combustion efficiency is generally high in CA engine. As I said, almost 97% of the total heat present in the fuel will be released. At the end of stage 4, only 3% will be lost in the exhaust. The exhaust will carry away the remaining 3% heat, which is not recovered in the engine. Okay, so this is how the different stages of combustion is happening in a typical CI engine. Next, we are going to bring out the factors that affect the stages of combustion. So one of the most important stage is the first stage of combustion, ignition delay time. So if you are able to govern the delay time appropriately, you can have some control over premix phase, because premix phase is dependent on the delay time. Based on how much of fuel is burned during the delay time, the premix phase, based on how much delay time is happening, the intensity of the premix phase is going to be different. Accordingly, the diffusion phase combustion is going to be different. So did you get what I am saying? So you have these 4 stages. I'll show it separately here. So you have stage 1, which is ignition delay. Then you have stage 2, which is premix phase. You have stage 3, diffusion phase. Then the final stage is afterburn. Now, when we talk about the duration of these different stages, all this dependent on the delay time, ignition delay time, okay? Because this happens one after other. Suppose if the ignition delay is longer, you will have more intense premix, very little diffusion burn, and then there is an afterburn, right? And you know, premix happens quickly. It's almost instantaneous combustion. So overall combustion duration will be shorter. So this is the overall combustion duration from here to here. Suppose if the delay time is shorter, the premix phase will also be shorter and diffusion will be longer. Then you have an afterburn phase. Okay. So this is with the increase ignition delay time. This is with the decrease ignition delay time. Based on the duration of delay time, premix, diffusion, and afterburn phase are going to be different. This is almost constant. The 10 to 15% of the final energy release is happening, and this generally happens after the end of combustion. So these 3 stages are intercoupled, meaning any change in ignition delay will affect the duration of this. This will affect the duration of diffusion burn. Did you get what I am saying?
Yes, sir.
Yes, sir.
Okay, so this is an important point to note down before we proceed and discuss the factors. That's why I've shown it separately here. So it means basically you can control combustion event in CA engine by controlling the delay time. There's no need to do anything else. Diffusion phase, as I said, you can control by controlling the rate of injection. So delay time is one of the most important phase. By controlling the delay time, you can control the overall combustion event in a CA engine. Okay, that's why it's very important to know the various factors that affect this ignition delay period. So these are the factors. The first one is fuel-based factor, cetane number. You know, this is playing a very significant role in affecting the delay time. Then you have injection pressure, fuel injection pressure. Fuel injection pressure is an operating variable. You can vary when the engine is running, you can vary this pressure, fuel injection pressure, and this is going to affect the ignition delay. Compression ratio is a design variable. Once you design the engine, you have to carefully fix the compression ratio such that you can achieve an optimal delay time. Engine speed and engine load are important operating variable. When the engine is running, you have to run at different speed and load. Especially automotive engines are subjected to various speed and load condition. So this is an operating, both are operating variable, and accordingly the delay time is going to be dependent on. Fuel injection timing is again an operating variable. In fact, you need to optimize injection timing in order to get the maximum benefit. And injection timing will have a significant effect on the ignition delay time. Then you have intake temperature. If you use any heating system, the temperature is going to be different, and also based on the ambient temperature condition, the intake temperature is going to be different, and this will affect the ignition delay time significantly. Then you have intake pressure. Pressure can be either ambient pressure in a naturally aspirated engine. It will be ambient pressure, which is almost constant and very low. If you use a supercharger or a turbocharger, the pressure, intake pressure is going to be different. This also affects the ignition delay time. So this is one of the important variable, ignition delay time, because it affects the startability of the engine. Suppose, especially under cold weather conditions. So earlier we discussed about cold start problem and how volatility affect cold start problem in a SI engine. Because in SI engine, you are introducing fuel under very low pressure and temperature conditions, right? Ambient condition, typical ambient condition, and cold weather will affect the startability of SI engine. In CA engine, we have a different problem. Under cold weather condition, you can expect that the ignition delay time is considerably high because the combustion event is based on self-ignition. Okay, for self-ignition, you need to have sufficient temperature inside the cylinder after you inject the fuel. Otherwise, ignition is not going to happen at all. Okay, suppose if the delay is too large, the engine may not even start. So you have to ensure that you are controlling this delay time so that the engine is able to start. That's where cetane number plays a significant role. You need to ensure that fuel has the required ignition quality defined by cetane number. We have seen in chapter 1 that is a minimum cetane number the fuel should have. Otherwise, the engine cannot even start. Okay, so ignition quality will play a significant role in affecting the delay time. This is one major effect. Second effect is the rate of pressure rise or knocking that happens in the CA engine is also based on the duration of the delay time. If delay time is very long, it's going to cause knocking event. We are going to discuss about that. The mechanism involved, we are going to discuss next. Okay, but just take a note here that the delay time is what is affecting the knocking because it is based on the rate of pressure rise. When pressure rise is increased beyond a limit, generally the 8 bar. It's bar per degree crank angle. That's a unit for dp by d theta. dp by d theta is the first derivative of the pressure profile. So when the value of dp by d theta is greater than 8 bar per degree crank angle, meaning that in one crank angle unit, the pressure rise is around 8 bar. If it is 8 bar or around 10 bar or so, you can expect knocking combustion. It's audible. I already discussed about the knock in SI engine. Okay, so during this period of time, there will be vibration in the engine. Okay, and other important signal is it is audible. Okay, the combustion noise will be high and it is audible to the human air. Okay, so this dp by d theta value will decide whether there is a significant vibration, whether the combustion noise is audible or not. Okay, so there is a threshold limit as I have indicated here. So it all depends on the delay time. So you need to properly control the ignition delay time. So you have two effects here, important effect in the engine. In fact, knocking will damage the engine as we know. So these two are primarily dependent on the delay time. As I said, cetane number is one of the most important variable. You have to ensure that you have a fuel with a minimum cetane number. I said about 40, right? So CN typically should be around 40 or above. If it is below 40, you will have a problem of startability, or you may have, even if the engine gets started after a long delay, you are going to have a very high pressurized rate. Eventually, there is a knock that happens in the CI engine. So this is one of the most important variable. It's a fuel-based variable. So, and this is an indication of ignition quality of the fuel. We already discussed about that. So ignition quality is defined by this property. So we ensure that fuel has the required ignition quality so that the delay is kept under control. So from the perspective of reducing delay time, the cetane number has to be higher. Then ignition delay will be shorter. This is what we want to avoid any knocking combustion. Engine should start smoothly. In order to ensure that, you need to have fuel with a well-defined cetane number, well above 40. Injection pressure, let us see how the injection pressure affect ignition delay time. So what will happen if you increase the fuel injection pressure? What will happen to the delay time? Increase or decrease?
Decrease, sir.
Ignition delay is going to decrease. What is the mechanism involved here? How the delay is decreasing?
Optimization will be better. So
Yes.
delay will.
Higher injection pressure, as you rightly said, will increase atomization. So when you are injecting at higher pressure, the rate of atomization, in simple words, it's about how smaller the drop size is. Okay. When I say finer atomization or better atomization, I mean to say that I have a very fine or small drop. If you have a very small fuel drop, then vaporization will be quick. So the rate of vaporization is primarily dependent on the size of the drop. The size of the drop is dependent on the atomization event that happens after the fuel is injected. When you inject at very high pressure, okay, the drop size is going to be accordingly very small. When you inject at a relatively higher pressure, the drop size may be higher. The higher drop size will result in slower vaporization. Please note that all these events are happening at a very small time scale, microsecond time scale. Okay, that is a typical time scale you need to remember always. So we have to inject at a higher pressure, ensure that there is a sufficient atomization. The drops are so small so that the vaporization event happens so quickly. Better vaporization will reduce the delay time because physical delay time is reducing, right? We talked about physical delay time. The effect of injection pressure is primarily on the physical delay time rather on the chemical delay time. Okay, so you will have a quick vaporization and you will form ignitable mixture quickly. And that time involved is called physical delay. Okay, so we prefer to have a high injection pressure to reduce the delay time because it reduces physical delay time. What about compression ratio? What will happen if I increase compression ratio?
The temperature and pressure of the combustion chamber will increase. And
so there will be increase of pressure and temperature inside the combustion chamber.
That is favorable for ignition to reduce the ignition delays in that way.
So this is going to reduce the delay time. By increasing compression ratio, I'm increasing pressure, temperature in the cylinder, thereby the delay time is going to drop. Okay, so we prefer to have higher compression ratio from the perspective of controlling ignition delay time, reducing delay time. Okay, so but generally, so you know the compression ratio will be in the range, right? In a CA engine, I said about it. So it varies anywhere between 14 to 22. You need to optimize it based on the given engine. Okay, you have a range of compression ratio. Okay, so you have to optimize it and ensure that you have a controlled delay time, right? A shorter one, not too long, which is what is going to create problem. But there is a problem in increasing compression ratio beyond a limit, upper limit. So what will happen if the compression ratio is too high? Any shortcoming with this?
So stress on the piston, it will increase.
Yes.
Mechanical durability actually in that way.
Durability will be affected. Higher the compression ratio, the engine will become heavier and heavier, right? So heavy weight, the stresses in the engine components will be so high, mechanical stresses. So engine has to be heavy to withstand that high stress, mechanical stress. That's why you will have a problem of lower mechanical efficiency when you start increasing compression ratio beyond a limit. So designers, so in SI engine, designers will try to increase compression ratio. The maximum value is limited by knock. In CI engine, the max value is limited by the mechanical stress that are produced in the engine. The engine will become heavier and heavier. Already you have excess air. The engine is bulky. So if you increase compression ratio, it will also become heavy. So designers of CI engine will try to restrict the compression ratio from this perspective. But the advantage here is you can control the delay time. You will ensure that there is a better startability. There is a smoother combustion, okay, by increasing compression ratio. Engine speed is an important operating variable. If you increase engine speed, what effect you can expect in the engine in terms of delay time?
So delay time should increase in my opinion.
Delay time should increase in crank angle or absolute time?
Absolute angle, sir, not on the crank angle.
Absolute time.
Yes, sir.
So delay time in absolute time unit will decrease. In crank angle or theta, it will increase. Delay time, when the engine speed is increased, you are going to have a better mixing, fuel or mixing, okay? That has a tendency to reduce the physical delay. The other important effect of increasing engine speed is the time available for heat loss is a function of engine speed. Okay, it's a function of engine speed. So when you run the engine at a higher engine speed, okay, so this is dependent on engine speed. When you run the engine at a higher running speed, okay, when this N is high, the time available for heat loss, will it increase or decrease? So this is inversely proportional. The time will decrease, okay. Higher the engine speed, the overall cycle time itself is less. Okay, the combustion event is consuming only a fraction of the overall engine cycle time. It's a very, very small time fraction of the overall cycle time. Okay, when you run engine at a higher RPM, the overall cycle time, the one engine operating cycle time itself will come down. And we are talking about combustion event, which occupies only a fraction of the overall cycle time. So the time available for heat loss is going to come down considerably when you are running engine at a higher RPM. Because of the less time for the heat loss, you are retaining more heat in the engine cylinder. When you retain more heat in the engine cylinder, how it affects the delay time?
It will reduce the...
Because you have more heat. When you inject fuel, when you have more heat in the cylinder, the overall delay time is going to come down. Isn't it? So one of the important effect of engine speed is you are not giving enough time for the heat loss. So you are retaining more heat inside the cylinder at higher engine RPM. That will reflect in shorter ignition delay in terms of absolute time. But what is also happening, I already talked about this, in a given time, the angle, crankshaft angle covered is a function of engine speed, right? When you run engine at a higher RPM, the angle covered in a given time is also more. When the engine spins at a lower RPM, the angle covered in a given absolute time is less. Did you get what I'm saying?
Yes, sir. Yes, sir.
So at higher RPM, you are going to have more crank angle in a given time. Okay, because of this effect, you will have in terms of theta, it will be slightly higher at higher engine speed compared to lower speed, whereas in terms of absolute time, it will be slightly less. Okay, so this is the effect of speed. Primarily, it affects the heat loss, time for heat loss. But what is also happening is the angle covered, the crankshaft angle covered in a given time is also a variable. Higher engine RPM, it covers more angle. Lower RPM, it covers less angle. So in terms of angle, it looks slightly higher. Ignition delay will be slightly higher, whereas in absolute time, it will be lower because of the heat loss effect primarily. Okay, so that's the effect of engine speed. When you talk about load, suppose if you are running engine at a higher load condition, load is defined by torque or power. What will be in cylinder conditions at higher load?
Temperature will be higher, sir. Temperature and pressure will be higher.
At higher load, pressure will be high, temperature will be high because you are burning more fuel at high load. Okay, as I already said, you are controlling load by varying the fuel mass. High load, you are injecting more mass, meaning you are burning more fuel. So at a typical high load condition, you will have a higher pressure and temperature conditions inside the cylinder compared to low load. So definitely this will reduce the ignition delay time. Since you have a higher operating temperature, pressure and temperature are high at high load, the delay time will be shorter. The opposite effect will be there at low load. At low load, you will have a lower pressure and temperature. Operating pressure and temperature in the cylinder is less. That will increase the delay time. Okay, so what we can say is ignition delay is a function of engine load. So if you plot ignition delay, so you will get a trend somewhere like this. It's a non-linear trend, but the trend will be a decreasing trend at high load because as the load increases, the pressure and temperature will rise. So when you move in this direction, pressure and temperature will be lower, so it will eventually increase the delay time as compared to the high load. So with increasing load, you will expect a shorter ignition delay time, not like a linear, you may have somewhat non-linear. Any engine trend is generally non-linear because it's a combined effect of many parameters. Again, please keep in mind that when we talk about effect of one parameter, we are capturing the effect of one parameter, keeping all other parameters as constant. That is how you will be able to capture effect of a particular parameter. You should maintain all other conditions as constant, vary only load. If you do that, you will see that the delay is decreasing with the increasing load. Primarily, it is due to the variation in in-cylinder pressure and temperature. It's time up. I stop here. If you have any questions, you can ask.
Professor Sir, Ramanand Yadav, today I am present. I just got 603.
Okay, fine. So you have taken a short leave for your marriage. Whether it went on well?
Yes, it's going well.
Okay, congratulations again.
Yeah, thank you, sir.
Okay, any questions?
Sir, on information, sir.
Yes.
Hello. Sir, next week, Wednesday, 5 to 6 is available, sir. Sir is not there. If you want, you can use it, sir. Okay.
Next week, you are talking about Wednesday 5 to 6. Okay, I will inform you if I am taking 5 to 6 slot. I have to check my other commitment during that time. Okay.
Sure.
If I am available, I will take that slot.
Right, sir. Thank you.
Fine. Okay, I'll stop here. I will meet you on Monday. Thank you.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you. Bye.
Thank you, sir.